These are additional book problems that I did not assign to help you with the vocab. This is number 73 in your textbook. Standard enthalpy change. Since we're looking for the standard enthalpy change, that is delta H reaction naught. For the decomposition of silver nitrate is given. Standard enthalpy of formation of AgNO3 solid is given. Calculate the standard enthalpy of formation of silver nitrite. So we know we're looking for silver nitrite. So the general equation is products minus reactants. So sum of all the products. So this is going to be N times the delta HF naught of the products minus summation of the moles delta H formation of the reactants. It's going to equal to the moles of AgNO2 times the delta H formation naught of AgNO2 plus the moles of O2 times the delta HF naught of O2 minus my reactants. My reactants are silver nitrate. So that's going to be the moles of silver nitrate times the delta HF naught of AgNO3. We know this reaction takes in 78.67 kilojoules of energy. So that is my delta naught of the reaction. So if I sub this in, this is going to be 78.67 kilojoules. This is equal to the number of moles of AgNO2. The coefficient of AgNO2 is 1. So this is going to be 1 mole of AgNO2. We are looking for the standard enthalpy formation of AgNO2. So we are looking for delta HF naught of AgNO2. This is added to the oxygen. If I look at my oxygen, it is at standard state. It is a gas on the periodic table at 1 atm and 25 degrees Celsius. So my oxygen will cancel out and become 0. Minus my moles of AgNO3. If I look at my balance equation, it is 1. This is going to be 1 mole of AgNO3. My delta HF of AgNO3 is given as negative 123.02 kilojoules per mole. So if I rearrange my equation and solve for delta HF naught of AgNO2, you're going to get negative 44.35 kilojoules per mole. And if you notice, since it's a negative sign, this is an exothermic, and so it's very stable. Here is number 81 in your textbook. Calculate the standard enthalpy formation of methanol. Again, we are looking for delta HF naught, and in this case, it is methanol, so CH3OH. Whenever we look for standard enthalpy formation, we get all those values from the appendix in the back of your book. If it's not on the appendix, it will be given to you in class, or you need to solve for it. So we know my general equation is going to be delta H reaction naught summation of the moles times delta HF naught of the products minus the summation and delta HF naught of the reactants. So my products are on the right side. So my equation now becomes moles of CO2 times delta HF naught of CO2 plus, because there are two products, moles of H2O times the delta HF naught of H2O minus my reactants, which is the moles of methanol times the delta HF naught of methanol minus, again, it is products minus reactants. So you could either distribute a negative sign, or after you do the math, you could carry the negative sign through. It's easier if you just distribute it as you write it in. So this is going to be the moles of O2 times the delta HF naught of O2. Already by looking at this problem, I already know one of the value is 0 because it's at standard state. So the delta HF naught of oxygen, because it's gas on the periodic table at 1 atm and 25 degrees Celsius, this will approach 0, so we could ignore it. So we are looking for this right here, so everything else is given. So if I look at this equation, the delta HF reaction is provided. It is 1452.8 kilojoules per mole. This is equal to the moles of CO2, which is 2 moles, times delta HF naught of CO2. Again, we get these values from your appendix, kilojoules per mole. We have water. The moles of water is 4 because the coefficient is 4. So this is 4 moles of H2O times the delta HF naught of water, which is negative 285.8 kilojoules per mole. Make sure you double check the states of matter because the values do change for the different states for every single element or compound. This is minus the number of moles of methanol, which is 2. So this is going to be 2 moles of methanol. And we are looking for the heat of formation of that. So delta HF naught CH3OH. Make sure you put the negative sign. I forgot to copy the negative sign through. Here, we do not have to divide by 2 for the delta H reaction because it is for this entire reaction, they gave it to you as negative 1452.8 kilojoules per mole. So solving for delta HF naught, rearranging and doing your algebra, you should get approximately negative 238.7 kilojoules per mole. So this is also exothermic, so that means it's very stable. This is number 110 in your textbook. We have standard enthalpy formation. So we are talking about delta HF naught is given for HF, OH minus, F minus, and H2O. First thing we're going to calculate is the standard enthalpy of neutralization of HF. This is an acid-base reaction because HF is a weak acid. OH minus is the anion of a strong base that has dissociated. And we notice this is a double replacement reaction. So I could select any strong base, such as LiOH, Li plus, and OH minus, and this will combine with F to create lithium fluoride, and that would dissociate into Li plus and F minus, and H will combine with OH minus to form water. And you could use any strong base cation and you'll still get the same reaction. And if you notice, the Li plus will disappear because it's a spectator ion. So this is an acid-base neutralization. So we're canceling out the moles of the HF and the strong base OH minus ion. We could rewrite this as delta HF naught reaction, or since it's a neutralization, this can also be H neutralization reaction. This will still be summation of the moles times the HF naught of the products minus summation of the N delta HF naught of the reactants. So this will be the moles of F minus times delta HF naught of F minus plus the moles of water times the delta HF naught of H2O minus the reactants, which is the moles of HF, times delta HF naught of HF minus, because it's also reactant, moles of OH minus ion, delta HF naught of OH minus ion. Now I'm going to plug in because all these values were given. So the fluorine ion has a coefficient of 1. So this is going to be 1 mole of F minus. The standard formation of F minus is given up here. So this is going to be negative 329.1 kilojoules per mole. There is 1 mole of water. The formation is given above is negative 285.8 kilojoules per mole minus the number of moles of HF. It is 1, so it's going to be 1 mole of HF. Enthalpy of formation is given above here as negative 320.1 kilojoules per mole minus the moles of the hydroxide ion. Again, there's the coefficient of 1, so it's 1 mole of OH minus, and this enthalpy of formation is given right here. So that's going to be negative 229.6 kilojoules per mole. It's negative 65.2 kilojoules per mole. Since it came out negative, this is an exothermic reaction and very stable. In part 2, it says using the value of negative 56.2 kilojoules as their standard enthalpy change of the reaction of the formation of liquid water, so H plus OH minus will produce H2O. Calculate the standard enthalpy change for the reaction. Now this becomes Hess's law. So what part B is telling you, this equation right here, the overall equation, which is the dissociation of the weak acid of hydrofluoric acid into its ion, occurs in 2 steps. The first step we calculated above. So I rewrote the equation. The top equation is what we solved in part A. The bottom equation is right here. I just recopied it. So this is Hess's law. The dissociation of hydrofluoric acid can occur in 1 step or in 2 steps. So we need to rearrange this equation so that the overall equation looks like one given right here. I pick the element or compound that's only present in the overall equation but not present in the other steps. So if you notice, HF is present in the top equation right here, but doesn't appear in the other equation. You don't want to use OH minus because it appears on the top and the bottom step. You don't want to use water because it appears on the top or the bottom step. You could also use F minus because it appears on the products. The first equation is written correctly. You want the HF on the reactant side and the F minus ion on the product side. If I look at my second equation, I know I need to flip the equation. Why? Number 1, HF present on the product side, but in the equation given, it is on the reactant side. In addition, we need to get rid of the OH minus that is on the reactant side of the top reaction. To do that, the OH minus must be on the product side to cancel out. Same goes with water. The water cannot be in the overall equation. It needs to be canceled out. We know that the first equation is correct. So that means to cancel out the water on the products, in the second equation, the water must be on the reactant side. So I need to flip this equation. So when I do that, I'm going to recopy it. So it's H2O yields H plus AQ plus OH minus AQ. When I do that, I need to flip the sign. Now it's a plus rather than a minus. Now I'm going to simplify. I'm just going to do basic algebra. I'm going to put all the reactants on one side and all the products on the opposite side and cancel out anything that is same on the both sides. There is only one HF, so I'm going to leave it as is. OH minus, I have one on the product side that will cancel out with the reactant side. That disappears. I have one water on the reactant side, which will cancel out with one on the product side. There is no more reactant. I'm going to draw my yield sign. I have a fluorine ion and a hydrogen ion. So if I look at my equation, my overall equation looks like the equation that is given above. And so now I need to add delta H's. So this is a negative 65.2 plus a 56.2 because we had to change the sign because we flipped the equation around. So we get negative 9.0 kilojoules per mole. To be successful in this chapter, you need to understand the vocabulary